அப்படியே போட்டுரு கீழே போட்டுரு சொல்லுமா yeah because the way I took the diagram, how was it? Can someone tell me the way I considered the diagram yesterday? How did I consider the diagram? Like, in which direction was the system revolving because of the forces? That's the reason. So, clockwise movements are, that's the reason. You know the answer. So, till what concept did we discuss yesterday? Is there any doubt till whatever we discussed? Eduma? Same thing she asked. Why did we take minus 2? It appears as if this move. Means that is the direction in which it is experiencing torque. Simple only. This fan is revolving off control. Near the direction. How is it getting switched on? Clockwise or anti-clockwise? Anti-clockwise. So when I switch it on, how is it revolving? Sorry, anti-clockwise now. Okay. That rod is there. Suddenly, if that breaks, okay, this fan will start coming down because it is already experiencing a torque in this direction. But who's holding it? The hinge that is there. Meaning, if you leave the system freely to rotate, it will start coming in the downward direction because of the anti-clockwise momentum. Simple monoline and the water bottle mechanism. Let's assume you are on lazy goose. Correct? Right? Sorry, never. You want to close this, you can do it like this also. If I'm tired enough, what I'll do is you turn it like this and leave. If you give enough amount of torque, what will happen? Automatically it will go and get screwed. That's the reason. Partially moving in the direction of torque is acting, but the system is fixed. Another, it will rotate like that. It will appear as if it is going like force torque. Breathe. Any other doubt? Is everything clear? What is the date today? 5 hours. யாராவது ஒரு அசிஸ்டன்ட் இருக்கா? கிளாஸ் வேலை. Here, one person is online. Stop you. Not sure who is online. So did they start this chapter in school? என்ன நடக்குது? Correction எல்லாமே. அப்படியே ஸ்கூல் ஓபன் பண்ணாங்க. என்ன பண்ணீங்க? ஒண்ணுக்கு. பிடி அதெல்லாம் பெரிய பாக்கியன்றியா? ஒண்ணுமே இல்லை, யாருமே இல்லாத கடைக்கு யாருக்கு ஆச்சு? அண்டர்ஸ்டாண்ட் தமிழோட? Ready? Shall we get started? Okay. சொல்லுமா. இல்ல இப்ப பாரு, பக்கா வரும் பாரு. நீ நேத்து பார்க்கல, இங்க டெக்னாலஜி புதுசா ஒண்ணு பண்ணிருக்கு. ஒரு நிமிஷம். நடுவுல பிரச்சனை பண்ணும். Even I'm getting used to it. Please give me some time. Hopefully in 1 week I'll be master in this. பாரு, திருப்பி பிரச்சனை. This was not on till now. காட்டிடுச்சு அப்படி சொல். நம்ம ஷட் டவுன் ஆகுதுன்னு சொல்றது. I thought it was on and I'm trying to push this formatting then. என்ன அவன் என்ன சொல்றான்? ஸ்விங் மோடு இல்ல, இது ஆல்ரெடி 17ல வைக்கவே கூடாது. ஸ்விங் மோடு வைக்கணுமா? இன்னொரு ரேசி அடுத்த வாரம் வந்துடும். இந்த ரூம் 23 I think this time. What is outside temperature? Did anyone see? 40 இருக்கா? 40க்குலாம் வெந்துருவோமா? Only problem with Chennai, no? Too hot. யார் ரிமோட் அம்சது பின்னாடி? That one will not be sufficient. இன்னொன்று வேணும். என்ன அங்க வெயிங்க. கல்பகேஷ், are you there? அவன் பேர் கல்பகேஷ் தானே?
Sir.
Why is he not responding?
Sir, கேக்குதா?
நீ கல்பகேஷ் இருக்கியா?
Sir, இப்ப கேக்குதா?
Yeah, can you speak now?
Yes, sir.
Okay, is the power PPT appearing big or small? சொல்லுமா. வேற எனக்கு இன்னொரு ஹெல்ப் பண்ணுங்க. கர்சர் ஒன்று சுத்திட்டு இருக்கேன். வந்து if it comes there, please tell me. I will be searching for it. கேமா எங்க இருக்க? எங்க இருக்க? It was down. It was here, no? எங்க ஓ இதுவா ஓகே yeah did we discuss this concept yesterday no right so till where did we discuss okay electric flux I explained no okay cursor please இது பாரு ஏதோ ப்ளே ஆகுது சரி ஒரே நிமிஷமா is it there it's very small and white no I'm not able to see it's there only yeah I came here சொல்லுப்பா and you not touch this okay see listen the next concept that we are supposed to discuss is about this charge distribution it's called so charge distribution right so till now we were discussing about the Coulomb's law and different kinds of systems right in all the systems if you see what was the nature of the charge that we took into consideration they were all point charges but it is not necessary that all the systems in this world is made up of only point charges right but one thing is clear that many point charges put together is going to give you a big charge right that we call it as an extended charge technically you call it as an extended charge see just to give you a simple understanding in your 10th grade right you would have learned this chapter light right in front of a mirror or lens you place objects right so when you talk about an object the object is of two types one can be a point object or it can be an extended object see for example if we stand in the front of mirror we can call ourselves as an extended object suppose you place a small object which is small compared to the size of the mirror itself you'll call it as a point object same logic okay so having said this when you talk about the nature or the way the charges are arranged right the charge distribution is basically classified into three types so obviously one is called linear charge distribution so linear refers to one dimension then you have surface charge distribution which refers to the two dimension and you have the volume charge distribution which is confined to the three dimension I hope it is clear right now said this if I take a see for example if I take this pen whose thickness is small whose thickness can be ignored but it is considered to be a straight line on top of this let's say the charge is distributed so when I say the charge is distributed it is going to be point charges right when you take all those things into consideration let me say the length of this material is L right and the sum of all these point charges put together is capital Q right if you are able to define the total charge per unit length what am I doing I'm calculating the total charge I'm dividing it with L I can call it as Q by L but how is it we are supposed to state it the total charge per unit length is what is called as linear charge density right so linear charge density is going to have the unit of Coulomb per meter it is amount of charge per unit length am I clear with this right similarly if you take surface charge distribution means let's say you take a paper on that paper the charge is distributed So where is the charge distributed now? It is occupying the area of that paper. Are you able to understand? So if you're able to define the amount of charge per unit area, you call it that as the surface charge distribution, right? Which is going to be measured in terms of coulomb per meter square, right? Similarly, what about the volume charge distribution? Obviously, the name suggests, right? You take a three-dimensional shape inside which you stuff the charge. The amount of charge distributed per unit volume. So only thing that is common is you need not memorize the statement. Anything you write in the denominator, what is the prefix you will add to it? Per unit. That's it. So amount of charge per unit length. Amount of charge per unit area. Amount of charge per unit. Makes sense? Right. So these are the three kinds of charges that are present. Sorry, these are the three kinds of charge distributions that are present. Right. This is important for us to understand. You're clear? No? Tell me. This one, huh? This one. Q is the charge. Charge can either be small q or capital Q. Sum of all the charges. Right. See, to put it simple, no, just to clear your doubt, let's say this charge is dq, this charge is dq, this charge is dq. Like this, I have multiple dqs. The sum of all these dqs put together is going to give me capital Q. It's not about an atom, no. See, if you take this material as a whole, it is neutral by default, unless you charge it. When you say you have charged the material itself, you're trying to tell someone that you have given excess amount of positive or negative charge. It cannot have both simultaneously. See, for example, if you take this object, rub it against some surface. Due to friction, what will happen? The charges get transferred from this material to the other. Right? Either of them is supposed to have excess amount of something. It can be positive or negative depending on the nature of materials. Yeah. Okay. So mostly what we do is we take these kind of charge distributions in the derivation part. So at that time, all the charge distributions are taken in such a way that each charge is uniformly distributed. What is the meaning of uniformly distributed? Means the distance of separation between each such point charge, which is summing up to the total charge, right? The distance between each such point charge is going to be a constant. Meaning, try to understand this, okay? 1 minute. So if I take this kind of a system, 1, 2, 3, 4, 5. For example, let's say there are 5 small such point charges. And let's say the length of this is going to be 10 units, whatever it is. Now, what is going to be the value of lambda for this case in terms of number? The total charge. So count each positive as 1 unit. So how many such units are there? 5. So 5 units are distributed over a length of 10 units. So what is going to be the value of lambda? It is going to be half coulomb per meter or whatever it is, unit per unit. Okay. Now, having said this, if I take this portion, how many charges are there? Right, 2. Means these 2 charges should get distributed over a length of 4 units so that I get the same half. That is the meaning of uniform distribution. Am I clear with this? So here the charges are uniformly distributed throughout the length, surface, or volume. Clear with it? So if you're done with it, I'll go to the next point. Shall I proceed? Shall I? So the next concept is called as Gauss law. Right. So like how you have this Coulomb's law to find the force. Is Coulomb's law applicable only to find the force? It is also helping us find something else. It is also helping us find the electric field due to a point charge, if you remember. E is equal to F by Q, but in the place of F, you applied Coulomb's law. KQ, Q0 divided by R square divided by Q0. Q0 gets cancelled. KQ by R square. Now, the question is, what if the system gets extended to being more than a point charge? Like if you have a linear charge distribution, for instance, then I'm interested to calculate the electric field due to this kind of a system. Right? So positive, like this, I take a system. Now, electric field is always calculated at a point. So if I take the point here, and if I take this distance to be R. Am I clear with this? So if I need to apply Coulomb's law and then solve this, what I'm supposed to do is, I'll give you a perspective of this. See, I need to take a small charge dq. Due to this dq, I need to find the value of electric field at this point. You understood why I drew the arrow mark away? Why is it so? Because it's a positive charge, right? So due to this dq, I'll find what is the value of the small electric field. It's also called as dE. Then I need to integrate it from one limit to another, which is slightly a tedious process. And as I mentioned, that is not a part of your syllabus as well, at least for CBSE. Right? Now, for these kind of charges, is there a possibility where we can take the help of symmetry and find the electric field in lesser number of steps? That is where this Gauss law comes into picture. Where the advantage of this Gauss law is, it takes the concept of electric flux into consideration. So there are two parameters that you need to know. One is you need to know what is electric flux generated due to the system, and what is the total amount of charge enclosed within a surface. The name of the surface, I'll reveal it. Okay, what are the two things? What is the amount of electric flux that is associated with the closed system, and what is the amount of charge that is present within the closed system? So having said this, let's first try to understand the definition of it. So what does it state? It states that it relates the flux. Here the flux means electric flux. Gauss law is applicable for electric and magnetic also. Okay, so there the flux would be magnetic flux. So listen to this carefully. The law relates the flux through any closed surface and the net charge enclosed within the surface. Right? I hope this point has got registered in your mind. So having said this, let's see how they are related. If you take the total electric field E over any closed surface, right? The total electric, there is a mistake here. It is not the total electric field, it is a total electric flux. Okay, correction. So the law states that the total, oh, I'm sorry, they mentioned flux here. Sorry, I didn't see that. What happened? Okay. So it states that the total flux of the, I need some more practice. It states that the total, what is happening? I understood what is the issue, but it will take some time to resolve. Pen came up. So the law states that the total flux of the electric field over any closed surface, this closed surface I told you, no, it is called as Gaussian surface. So the total electric flux over any closed surface is taken to be equal to 1 divided by epsilon naught. Okay, epsilon naught is the permittivity of free space. 1 by epsilon naught times the total charge that is present within the closed surface. It's a simple statement. You know the total flux through a closed surface. You know what is the total charge through the closed surface. Okay, so that's what they told, no? How is flux represented as? With the symbol phi. So if you know the total flux through a closed surface, this will be equal to what? 1 divided by epsilon naught times the charge enclosed by the Gaussian surface. This is the mathematical statement. With this, you will see you can find the electric field in very less number of steps. Okay. So this flux is there. Now, what is the formula I told you yesterday? It is E vector dot A vector. E vector dot A vector is equal to charge enclosed divided by epsilon naught. Right. Now, I want to introduce one more thing here. See, this E dot A, you can write it if you directly know the value of electric field and you know the value of the aerial vector. Right. But there will be scenarios where you don't know the aerial vector completely. At that time, what we are supposed to do is flux is written as something like this: integral with a circle around it, which we call it as loop integral. So when you talk about integral, no, there are two things. One is like this, which is called as line integral. This is what you would have seen in your 11th standard when you derive the formula for equations of motion. It's called as line integral, whereas this is called as the loop integral. So, or surface integral. So it's called as surface integral or loop integral. It is given as E vector dot, instead of A, right, you will have dA vector. So the surface integral of E vector dot dA vector is also going to give you the total flux. This is what we are going to use in the applications of Gauss law, which I told you yesterday. There are 3 applications I told you, no? There we'll use this expression. Am I clear with this? But everything relates to the same concept of flux. So can you people tell me the statement of it? Just put it in one line and tell me the total electric flux through any closed surface is equal to 1 divided by epsilon naught times the charge enclosed by the closed surface. That's it. Okay. So this is the mathematical expression. Write it. You will integrate the area itself. Generally, when you put a line integral, you get area. Line integral output is an area. Similarly, loop integral's area will be volume. Double integration, Mary, but it is not like actually loop integral. I'm sorry, I have to correct. This is you're integrating the area itself. There, you're integrating one dimension. For example, you will integrate something like lambda dx. X refers to length. Okay, you're integrating a one-dimensional parameter, whereas here you're integrating a two-dimensional parameter. Okay, so when I do the derivation, you will understand how the values will come. Yeah. You're clear? Shall we proceed? Yeah. Done? Okay. So we discussed about the closed surface. No? That what is the name of the closed surface? We call it as a Gaussian surface. Right. So basically, this is something that does not exist. It is something that is imaginary. It is an imaginary surface which is drawn around the charge distribution that is given to us. So whatever is the shape of the charge distribution they have given. See, we discussed about three main types. Those are all uniform charge distribution, but there is a possibility where something can be non-uniform also. Like you can have a charge that is distributed in some shape like this, who knows? Right? So when you have something like this, right? For us to apply the Gauss law, we need to consider a closed surface, right? And that closed imaginary surface that we consider is what is called as Gaussian surface, and mostly it is a three-dimensional field. It's mostly a three-dimensional shape, right? And here, see, if you read this node, right, one point that we need to concentrate upon is Gauss law tells us that the flux through any closed surface S, if you name the closed surface as S, depends only on the value of the net charge inside the surface and not on the location of charges outside the surface. So, sorry, and not on the location of the charges. And the next point is charges outside the surface will not contribute at all. Listen to this point carefully. What I'm trying to say is, if I say I have a point charge like this, if I take a closed surface like this, which I call it as the Gaussian surface, then this is going to have the field lines in this way. Am I right? Right. So here, if I take the sphere of radius r, let's say the flux is coming out to be phi. Now my question is, what will happen to this flux if I increase the radius of the sphere from r to 2r? So logically, what should happen? Flux should decrease. How many of you say decrease? Okay. Whatever is your gut feeling, just raise your hand. You're saying decrease. How many of you are saying increase? What are the others saying? Don't know. Jesus will take care. Huh? Nothing should happen actually. It should not change. It should not change. So if this is R, if you increase the size of the Gaussian surface to whatever value you want, it is still going to be the same. Because you can apply two logics to it. One is, you see the number of field lines that are going is the same. I know where you got confused. Thing is, if I take my hand and keep it like this, that area, if I keep moving, it will change. But this Gaussian surface is considered in such a way that it is covering the whole charge. That is what the first point says. So there is one often asked question, right? They often ask this. And most of them write it as 2 phi. No. Flux has nothing to do with the radius of the Gaussian surface, the size of the Gaussian surface. What does it depend on? It depends only on the total charge that is present within the Gaussian surface. If it is Q, and due to this Q, if there is a flux that is going to get generated, according to Gauss law, what will be the value of flux that will get generated? Charge enclosed divided by epsilon naught. So, is there anywhere this flux is dependent on the radius mathematically? Nowhere. What does it depend on? It depends on epsilon naught, which is a constant, and Q is the total charge, which is inside the surface. Similarly, if I have a system like this, if I have a positive charge here, if I have a negative charge here, then what is going to be the total flux through the surface? If I take the value of this as Q1, if I take the value of this as Q2, for instance, then what is going to be the flux in this scenario? It will be Q1 divided by epsilon naught plus minus Q2 divided by epsilon naught. Am I right? What is the second point saying? It depends only on the charge present inside. Outside charge has nothing to contribute to the flux. Common mistakes. So what should be the answer? Q1 by epsilon naught should be the answer. Right? One last question. So if I take this kind of a system, Q1, Q2, Q1 positive, negative Q2, positive Q3, right? And outside you have Q4 and minus Q5. What is going to be the total flux through this kind of a surface? Q1 minus Q2 plus Q3. That's it. So what did you apply here? You applied some property. What is the name of this property? It's additive nature of property. I told you, you'll apply it at the later part of the chapter. So additive nature of charge divided by epsilon. So outside charges, we are not concerned at all. Let it be infinite number of charges also, right? These are two important points you need to have in mind. Did you understand the application of these 2 points? Make a note. How can we talk about flux? For a 3-dimensional shape, you mean to say there is no curved surface area? We don't take volume, no? For example, here I considered a sphere. Now, the next step I'll explain. You will understand. Then yeah. Shall I proceed? Yeah. Shall I proceed? No? Yeah. So next is something important that we are going to see. The steps that we need to follow to apply this Gauss law. It has 3 applications. No, she wants to copy you. Okay. Yeah, finish it first. No, you're done. No? This one. So let's see what are the steps to apply this Gauss law, right? So these steps, as I told you, we can apply it to any surface. So first thing is define the type of charge density. What is the meaning of it? Depending on the nature of charge distribution that you have, you need to define the charge density for that. Okay. So what I'll do is I will take an example that we already know, right? for which we already know the result, and then apply these steps and show you. So parallelly, I'll be finding the electric field due to a point charge. So what is the electric field due to a point charge at a distance r from it? It is kq divided by r square. Right? This is a known result, but the kq by r square, we derived it using Coulomb's law. Now we'll derive it using Gauss law. So first thing, due to a point charge, first thing is I have a point charge. Right? So is there any type of charge density you can define for this? No, because it is just a point charge. Second is, consider a Gaussian surface around the charge distribution, right? And ensure it passes through the point where the field is to be calculated. Suppose I'm interested to calculate the field at this particular point P. Now, I need to consider a Gaussian surface which is symmetrical to this. So with respect to a point, what is the symmetric shape that you can get? Meaning, this point P could have been here at a distance r, or it could have been here at a distance r, or it could have been here at a distance r. Like this, it can be anywhere. If you join all these points, what is the shape you are going to get? You get a circle. But this point can be here. This point can be at the back of the board also. Meaning it should be a sphere. Am I clear? So one more important point, what is it we need to consider? You need to ensure that the Gaussian surface is always passing through the point where the field is to be calculated. So you need to take the Gaussian surface in this case to be a sphere of radius r. Third point. We need to consider a small area dA on the Gaussian surface. Suppose the sphere is like this, right? If I take this knuckle, for instance, right, this will be a small area that is present on the sphere. So what I'll do is I'll consider a small area here and I'll assign the value to it as dA. Am I clear with the third step? Right. And what is the dA, and assign direction to it. So with respect to the aerial vector, what is the direction? It is always in the radially, yesterday I told you, it is always in the radially outward direction, right? Meaning I should take it like this. So that is the direction of aerial vector. So first step, second step, third step is over. Fourth step is find the direction of electric field through the small area dA that we have considered in step number 3. So due to this charge distribution, due to the positive charge, what is going to be the direction of electric field through this small area dA? So when you draw the field lines for it, how is it going to look like? It is going to be outward like this, among which one such electric field line will pass through this, right, which I call it as E. Remember, E and this dA are parallel to each other. E and dA are parallel to each other. Now what you're supposed to do is find the total charge enclosed in the Gaussian surface. What is the total charge enclosed by the Gaussian surface? Only one charge, Q. So is it clear till the fifth step? Right? The next two steps, what is it? Apply the surface integral of E dot dA is equal to Q divided by epsilon naught, solve for the electric field. So we are almost at the end. So what is that I'm supposed to do? The surface integral of E vector dot dA vector is equal to the charge enclosed divided by epsilon naught. What did I apply here? Basically, Gauss law. The total electric flux is equal to 1 by epsilon naught times Q. Right? What is the angle between E vector and dA vector? 0. Right? When it is going to be 0, then can I write this as E into dA is equal to Q divided by epsilon naught? Right? The value of electric field is constant at a given distance. So if I take this dA anywhere on the surface, the value of electric field would have been a constant. So I need to take the constant outside. So what will I write it as? E into the surface integral of dA is equal to Q divided by epsilon naught. Makes sense? You know, right? In differentiation integration, you can take out the constants, right? Now see, E is okay. What is the surface integral of this dA? This is what we need to understand. On the three-dimensional shape, on the sphere, if you take all such dAs and add it, integration is basically adding. On that surface, if you take all such dAs and add it, what is it you're going to get? You will get the bigger area. What is that area? It is going to be the surface area of the sphere. And what is the surface area of a sphere? 4 pi r square. Where did I keep? So I'll write it in the next page. So E into, I'll write this again, E into integral of dA is equal to Q divided by epsilon naught. E into, what is going to be the surface area? 4 pi. What should be the value of R I should take? That is the radius of the Gaussian surface itself. So which is going to be small r square is equal to Q divided by epsilon naught. So what is the value of electric field? Q divided by this 4 pi and epsilon naught I'll combine. This R square I'll write it separate. We're able to understand. It's the same thing that we derived in a different way. Right? So this example I took only for you to understand these steps. Is it clear? Right? No. Which one? This step. You didn't understand why that. This one you are clear. Yeah. So if you take a sphere, you took the dA on that sphere, right? Like that, how many such dAs will be there? Infinite. If you add all those dAs, so if you integrate all such dAs, what will you get? Meaning, if you take a sphere, okay, let's say I give you a brush. With a brush, you are placing a dot on. You dip it in a paint, put one dot, you get dA. Similarly, you put another dot, you will get dA. Like this, if you put infinite number of dots, what is the area you are covering? The outer surface, no, of the sphere, which is 4 pi r square. That is the reason I took 4 pi r square. Right? So this is going to be the answer. Please make a note of it. So when you're writing, in your book also, I would suggest write it in the landscape mode. Turn your book like this, and like write in the way I wrote it. Okay. Right. So there are 3 more concepts left. See, as I mentioned in the previous class, right, since to save time, what if I record them and send it? Will you guys work and come by Monday? The maximum, each topic will be for 10 minutes. That's it. Each application will be for 10 minutes. If you can spend 30 minutes of time, take down the notes and come. Monday, I want to sit and solve problems. The first 15 minutes, I'll give you time to clarify your doubts from the videos that you have gone through, right? And then we'll sit and solve the problems. Maybe till Tuesday, we'll do it. So leaving the next week, the week following it, you will have a test in this chapter. Okay, so be prepared for it. It will be the pattern which was announced last year. You'll have a combination of MCQs, assertion reason based questions, case study based questions, and subjective. Paper is already prepared. Only thing you have to come and be prepared to write it. Is it clear? Right. So I'll be sending you the recordings for it. Right. Just go through it. Take down the notes. Just don't go through. Take down the notes. Come in the next class. If you have any doubt, you can ask. By the way, like those who are already there with us last year, you will know. For those who are new, this is the number on which you can reach out. Okay. For any doubts that you have. So you would have got numbers related to whom to contact for app related issues, right? Similarly, whenever you get a doubt, reach out to this number. Right, 6369210899. Drop a WhatsApp message, we'll get back to you. Is that clear? So any other doubt from today's class? Oh. This is all for today. Time 5/7 today.